Alright folks, welcome back to another computer science video. Today we talk about computer scientist Dijkstra. Come over here real quick, let's look at this guy. Alright, so here we got the Wikipedia page for our boy Mr. Dijkstra. Let's look at what this guy's done. Look at this, like 1,000 different algorithms. This guy overpowered, man, basically invented computer science. Well, today we're looking at that algorithm named after him, Dijkstra's algorithm. Alright, let's get into it. Alright kids, today we're talking about our boy Dijkstra's algorithm. So the first thing that we have to review is how a graph works. We know that a graph is made out of nodes, which are like these locations in the graph. So for example, SF is a node and Seattle is a node. These nodes are connected by edges, and each of these edges has a number next to them, and that number is a weight. The bigger the weight is, the more expensive it is to get from one node to the other node that the edge connects to. So for example, it's more expensive to get from SF to Seattle than it is to get from Seattle to Idaho, because the weight for this edge is greater than the weight for this edge. Alright, so that's graphs for you. What Dijkstra's algorithm does is it finds the shortest path to get from one node in your graph to any other node in your graph. So for example, let's say we're core college students, we're going on a road trip. We want to go from San Francisco to New York City. We want to find that shortest path to get from here to here. So this is our start node, this is our end node. Well, we can see that there are a crap ton of ways to get from our start node to our end node. We could go from SF to Idaho to New York City. Let's just write out the total path cost. So we know that it's 5 to get from SF to Idaho, plus another 1 to get from Idaho to NYC. Total path cost is 6. That seems a little bit high, and since we're poor college students, we want to save some of that gas money. So let's see if there's a shorter path. Well, we see that, let's say we go up from SF to Seattle first, so that's a cost of 3. We go from Seattle to Idaho, cost of 1. And then we go from Idaho to NYC. That's a cost of 5, and that's actually lower. So the shortest path in this case, and in this case, this is the shortest path in our graph to get from SF to NYC, is to go from SF to Seattle, Seattle to Idaho, and then finally from Idaho to New York City. You'll notice that even though in our first case, we only went through 2 nodes to get to NYC. In our second case, we had to go through 1, 2, 3 nodes. But even though we went through 3 nodes, our total path cost is still lower. And Dijkstra's algorithm will always find us the shortest path, no matter how many nodes that we go through, as long as all these weights are greater than or equal to 0. Alright, it seems like our boy Dijkstra is saving us a lot of that cash money. Let's see how this guy does it. Let's do it. Alright folks, now we're coming at you with the Dijkstra's algorithm example. So over here we got a graph pretty similar to the one from before. Some of the edge weights have been changed, but Dijkstra's algorithm will still run on it correctly. Alright, so now let's talk about the 3 essential components we need in order to make Dijkstra's algorithm work. Let's start with this one down here. So we have a minimum priority queue. The main core of how Dijkstra's algorithm works is that we add our start vertex, and in this case we just chose SF, we put it into the minimum priority queue. And the priority we assign it is the distance of that node from the start node. In this case, the start node is 0 away from itself, so we just give it a priority of 0. At each step of Dijkstra's algorithm, we remove the smallest entry in our minimum priority queue from our minimum priority queue. Then we add all of its neighbors, which are the nodes that are directly connected to it. So if we removed SF, for example, we'd add Seattle and Idaho. Every time we remove a node, we add it into our visited nodes list. If a node is already in the visited nodes list, we don't check it if it's the neighbor of a node that we just removed. Might seem kind of confusing, but let's go up here really quick and check out this table. So this will be used to track the shortest total cost to get to each of these nodes. So you notice in this first column over here, we've listed the names of all of these nodes. Over here, the third column it'll be used to track the node that we have to come from in order to achieve the shortest path. So for example, if the shortest path from SF to Chicago requires that we go from Idaho to Chicago, then over here for Chicago, the previous node, we'd write down Idaho over here. Alright, let's just get into the example and see how it goes from there. So first of all, in our minpq, remember at the beginning we just add SF because it's our start node. And we give it a priority of 0 since it's 0 from itself. So we have that. And we also update it in our table, so we see that SF is 0 from itself. Previous node, we can just say itself. Alright, so since it's the smallest entry in our minpq and the only entry, we get rid of it. As soon as we get rid of it, we can add it to our visited nodes list. And then we add all of the neighbors of SF that are not in our visited nodes list. So that's Seattle, and it's a total cost of 3 from SF, and we see Idaho total cost of 5 from SF. Okay, and then we update those in our table. So we see Seattle is 3, it comes from SF. We see that Idaho is 5, and it also comes from SF. Alright, so now we scan our min-PQ, look for the minimum smallest priority element. So we see that Seattle, we remove Seattle, we add it to our visited list, and then we know Idaho is still going to be our min-PQ, so we just copied that down into the next step with this priority of 5. And now we check all of Seattle's neighbors to see if we should add them to our min-PQ. So over here we got Seattle, we see it as 3 neighbors, so the first neighbor we check is SF, we see SF is in visited nodes already, so we just ignore it. Then we check Idaho. So we see Idaho is not in our visited nodes list, but it is in our min-PQ. So over here, this means that we found a potentially shorter path to get to Idaho. In this kind of case, we have to check if this new path is shorter than the path we have already, and we either accept this new path or we accept the old path. So let's check this out. We know that according to our table, Seattle is 3 away from SF, and then this is the shortest path to get to Seattle, so it's 3. And from Seattle to Idaho, we know that's a cost of 1. 3 plus 1 is 4, and 4 is less than 5. So it means that our new path is shorter than the path we have already to get to Idaho. So in this case, we would update the priority of Idaho in this case to 4. We'd also update that in our table, so this 5 becomes a 4. This SF would become Seattle because it now comes from Seattle. And then after that, we just resume checking all the other neighbors of Seattle. So we only got one neighbor left, that's Chicago. We check our visited nodes list. Chicago's not in there. It's also still not in our min-PQ. So we just add Chicago as usual. And we know that the shortest cost we know of to get to Chicago is the shortest cost to get to Seattle, which is 3, plus the cost to get from Seattle to Chicago, which is 2. And 3 plus 2, that's 5. Alright, so now we check our min-PQ. We find the smallest element, that's Idaho, we get rid of it, we add it to our visited nodes list. And before we forget, we know that the shortest cost to get to Chicago right now is 5, and it comes from Seattle, as we found in the last step. Alright, so we've gotten rid of Idaho, we copy down Chicago because we know it's still in our min-PQ during this step. And now we check all of Idaho's neighbors. So we know Idaho has basically all the nodes in the graph as neighbors, so we check all 4 of them. So SF we see as our visited nodes list, we ignore it. Seattle, also in our visited nodes list, we ignore it. Chicago, it's still in our min-PQ. So we check if this new path is shorter than the path we have already. So the shortest path we know to get to Idaho is 4, and the path to get from Idaho to Chicago, that's 3. So 4 plus 3 is 7. 7 is greater than 5, which means that the old path that we had is actually better than this new path we found. So in this case, we just ignore the new path and continue checking the rest of the neighbors. So we just keep this old priority of 5. So NYC, we see it's not in our visited nodes list. It's also not in our min-PQ. So all we gotta do, add NYC. So NYC, and we know its priority has to be the shortest path to get to Idaho, which is 4 plus 6, and that is 10. And we can update that in our table. We know that it comes from glorious state of Idaho. Okay, so now we check our min-PQ again, find the smallest element is Chicago. We add Chicago into our visited nodes list. And we copy down NYC because we know it's still got to be in our min-PQ. And then we check all of Chicago's neighbors. So it's got 3 neighbors. We see Seattle is in our visited nodes list, so we ignore it. We see Idaho is in our visited nodes list, so we also ignore that. And NYC is still in our min-PQ, so now we see if this new path is shorter. The shortest path to get to Chicago is 5, which we found already, and we know that because Chicago's already in our visited nodes list. And to get from Chicago to NYC is 4, 5 plus 4 is 9. 9 is less than 10, means we found a shorter path. Alright, so now we update the priority of NYC. The 10 becomes a 9, we go up here, NYC, boom, 10 to a 9. Idaho, we know that this new path comes from Chicago, because we just removed Chicago. So the previous node for NYC is now Chicago. And finally, we have checked all the neighbors of Chicago. NYC is still the only element left in our min-PQ, so we remove it. And all of its neighbors, Idaho and Chicago, are both in our visited nodes list, so there's nothing to add. This means that after this step, our min-PQ is empty, and this means that we have finished Dijkstra's algorithm. We can double check this because we know that at this point, after we remove NYC, remove that to our visited nodes list, we see that every node in our table is also in our visited nodes list, which means we've successfully processed each node in our graph. But how do we get this table representation to actually represent the shortest paths? Meaning, which nodes do we have to go through in order to from SF in order to get the shortest path to NYC, for example? We don't know if we have to go through Seattle, or we have to go to Idaho, or we have to go to Chicago. Turns out all that information is in this previous node column and this total cost column of this table. So let's make sure that makes sense real quick. So the first thing that we have to draw is SF, which is our start node. Then we see that Seattle has a total cost of 3 away from SF, but it comes directly from SF. So we know that there's only one edge connecting them, and it has to be of weight 3. We know that Seattle is directly connected to SF, so the shortest path to Seattle from SF looks like this. Okay, let's do that for Chicago too. We know that the total cost to Chicago is 5, and it comes from Seattle. We know that Seattle is 3 away from SF, so 5 minus 3 is 2. So we know that Chicago is 2 away from Seattle. Alright, we know that Idaho is 4 away from SF, and it comes from Seattle. We know Seattle, again, 3 away from SF. 4 minus 3, that's 1. So we got Idaho coming over here, and there we go. Alright, we got NYC, final node. We know that it's 9 away from SF. It comes from Chicago. Well, we go up in our table, our very helpful table, and it says that Chicago is 5 away from SF. So 9 minus 5 is 4, which means that NYC is just 4 away from Chicago. Finally, our final step, we just got to make sure all of these edges actually exist in the given graph. So we see these two match up, these two match up, these two match up, and finally, these two match up. Alright, this means that we've successfully constructed a shortest paths tree. And all that is a visual representation of the shortest path from our start vertex, or start node, which is SF, to every single other node in our graph. So we see that this is the shortest path to get from SF to Seattle, SF to Idaho, SF to Chicago, SF to NYC, all in one picture. And that's all a shortest path tree is. And Dijkstra's allowed us to do this. It allows us to create this table. It allows us to create this representation. That's some good stuff. We found the shortest path from our start node to every single other node in our graph. Alright, but how does this work, and what would the code look like? Well, let's find out in the following sections. Let's go. Alright folks, so we've built up a little bit of an idea of how Dijkstra's algorithm works. Now let's talk about why it works. I'm going to go through a couple of examples that I hope gives you a better idea of how the algorithm works. It won't be a comprehensive mathematical proof. I'll put a full proof down in the description. But I hope these examples will help you get a better idea of why Dijkstra's works the way it does. Alright, so we've got the same graph as we used in the previous example. Start node is still SF. Remember that two of the big components of Dijkstra's algorithm that we're going to use are a min, pick, q, and then we're also just going to put the visited list down here. Alright. So first of all, we know that we add the start node to our min, pick, q in the beginning. So SF, and it has a priority of 0. Then, at each step of Dijkstra's algorithm, we remove the item with the smallest priority from our min, p, q. So we remove it, and then we add all of its immediate neighbors. So then we add Seattle, that's got a priority of 3. Then we also add Idaho, which has a priority of 5. Alright. So we know that in this case, we'd remove Seattle after this, and then we'd put, since in this first remove of SF, we add SF to visited, then we add Seattle to visited. Okay, this means that we've found the shortest path to SF, and we've also found the shortest path to Seattle. But why is this the shortest path to Seattle? What if there was some other path, and how do we know we haven't explored that path? Well, let's say there was a shorter path to Seattle, and we'd have to draw it out really quickly. Let's say there was a node over here. Let's call that A. Well, let's say there's a path edge of length 2.5 from SF to A. Let's just write that out and make that look a little bit nicer. 2.5. Okay. So let's erase this min PQ. This step would still be about the same. We wouldn't remove Seattle just yet, but its priority would still be 3 the first time we add it. And then we would also add 5. So this is one entry, this is another entry, and then A is a distance of 2.5 away from SF. Alright, so we got these 3 entries now. Notice that since A is the smallest entry, then we remove A, so we know we've found the shortest path to A. Well, What if A connected directly to Seattle? Would it be a shorter path from SF to Seattle than this original path over here? Well, let's say this was 0.4. Let's put that cap over here. Then in this case, after we removed A over here, we would update Seattle. Because we know that this path, all of A's neighbors, A only has one neighbor. It's Seattle. And we know that Seattle is already in our min PQ. So in this case, for our next step, Seattle would still be in our min PQ. It would have a value of 3. But now we found a new path, which has a value of 2.5 over here, 0.4 over here, total 2.9, which is shorter than 3. So we update the priority of the shortest path that we know that goes to Seattle in our minimum priority queue. So the only time that there would possibly be a shorter path than this direct path from SF to Seattle is if this other path has a total cost of less than 3. We know that the first edge in that path has to have less than 3. Otherwise, it will be confirmed longer than this path. This is because if this was 3, then this path, since it's greater than or equal to 0, must be at least 3. And this path is already 3, so we don't need to consider that path. Like for example, if this was 3 and this was 2, this path has to be longer than this path. But in this case, since 2.5 is less than 3, then this could potentially be a shorter path. Because we know that the total cost of this path is 3, this one starts at 2.5, and if this edge over here has a weight of 0.5 or less, then this path could be shorter than this path over here. But let's say this wasn't 0.4. Let's say it was 99. Well, we'd still have a similar setup, so let's get rid of this really quickly. We know that we'd still get rid of SF in the beginning, then we'd add Seattle, Idaho, and A. A still has the smallest path away from SF, so then we get rid of A. Then we see Seattle's already in our minimum priority queue. We check if this new path is longer than or shorter than our original path. We know that this original path has a length of 3. This new path has 2.5 plus 99. It's got a length of 101.5. So we know that that path is not as good as the path we had already. But since we stored the path already over here, we don't need to make any more changes. So by the time that Seattle gets removed, we know that we found the shortest path. So the lesson here is that Dijkstra always removes the smallest cost entry from our minimum priority queue. This means over here, even though we put Seattle already in our minimum priority queue, if we were to find the shortest path to Seattle, we'd still have to explore this path over here. Because 2.5 is less than 3, 2.5 also less than 5. It's the smallest entry at this step in our minimum priority queue. Because it's less than 3, which is the direct path from SF to Seattle, this could be a shorter path to get from SF to Seattle. We saw that if this edge were 0.4, 2.5 plus 0.4 would be less than 3. So this path from SF to A to Seattle would actually be shorter than this direct path from SF to Seattle. But in the case that this was actually 99, this new path would have an edge weight of would have a total cost of 101.5, which is greater than 3. Either way, we've already stored the original path that we found over here. We still have to explore this one. We're curious. We want to see if this path is actually going to yield a shorter total cost than this path over here. So we explore it anyway. And Dijkstra allows us to explore these possible paths. Because regardless of how long these eventual edges are, we still know that 2.5 is less than 3 and 2.5 is less than 5. We don't know the value of this weight over here, but since we know that this is already less than 3, it could potentially be a shorter path. So Dijkstra forces us to explore this before we remove Seattle from our min PQ. Okay, so this means that Dijkstra's algorithm always forces us to check any potentially shorter paths to a node. Like over here, we know that there's a path from SF to Seattle. We know that length is 3. It could be the shortest path. It might not be the shortest path, but it's the shortest path that we know of at this moment. There's potential for a shorter path over here. There's no potential for a shorter path over here because 5 is already greater than 3, and since the edge weights are greater than or equal to 0, the path can't decrease in length going from Idaho to Seattle. So this is the best path that we know of. This is a potentially better path. And depending on how many nodes and the total cost of all these edges that go from A to Seattle, this might be a better path, might not be a better path. Either way, by the time that Seattle is removed from our min PQ, we've already checked this path and we've already compared it with this path, and this would extend to, if we had multiple paths to Seattle, all of those possible paths that could be shorter than an original path will have been checked, and we'll finally end up with the shortest path out of all of them to get to Seattle. And this logic applies to every single one of these nodes, and that's why Dijkstra's works, because it forces us to check these paths that could potentially be of a shorter distance from the start node to the node that we want to get to. Alright, hopefully those examples helped your thinking a little. We'll jump into some code implementation now, and hopefully it all comes together. Let's do it. Alright folks, so now we're hopping into a code implementation of Dijkstra's algorithm. This is pseudocode, remember, so it won't actually work, but it conveys the main ideas of how this algorithm works. So make sure you follow the highlighted line, and let's go. So the first line says, this is Dijkstra's algorithm. We take in a graph called graph and a node called start, which is just our start node. After that, we make a map from node to int called total costs. It basically connects each node with the shortest path cost or the shortest path length from the start node to that node. The second map we make is from node to node. It records which node we had to come from in order to create our shortest path. Third thing that we make is our min-pq, self-explanatory. Fourth thing we make is a set of nodes called visited. What this is basically our visited nodes list from the example. Except we used a set simply because it's a little faster and more efficient. But otherwise, it does the same thing as our visited nodes list. Alright, so after that, we put our start node into the total costs map with a value of 0. We add the start node to our min-pq, and then we go through every node in our graph. As long as that node is not our start node, then we put it into our total costs map with a value of infinity. Keep in mind that by the end of Dijkstra's algorithm, we'll go through every node in our graph, and its value will be set to some total path, set to its shortest path cost or length, and it has to be less than infinity. So all these values will be changed by the end. Then we go into the main loop of Dijkstra's algorithm. So as long as this min-pq is not empty, we remove the smallest item from our min-pq. We check all of the neighbors of the element that we just removed. As long as that neighbor is not in our visited nodes list, we find the length of the path, the shortest known path from our start node to that neighbor node. So we do this by finding the current shortest known cost from our start node to the node that we just removed, plus the shortest known cost, or plus the shortest known cost from the node that we just removed to its neighbor. Alright. Now we check if the path that we just found is shorter or has a less expensive cost than the existing path for that neighbor. And if it does, then we update that in our maps with the new shortest cost or length, and then we decrease the priority in the min-pq of that neighbor, which now has a priority equal to the length or the cost of this new path called alt path. Alright, so we continue this as long as the min-pq is not empty. After it's finally empty, which means we finished Dijkstra's algorithm, we create a list called results, we add our two maps into it, and then we return that list. So just a quick summary, remember that results will contain total cost, which is a map of each node to the length or the cost of the shortest path length of its shortest path from the start node, and previous nodes will be a map of each node to the node that it immediately comes from in order to create the shortest path. So using these two, you can create a shortest paths tree. You can figure out which node that you have to go to or come from in order to get the shortest path from your start to whatever node that you want. Alright folks, and that is Dijkstra's algorithm. Hope you learned something, and as always, good work, good stuff as usual. Alright folks, thanks so much for watching this video. As always, if you enjoyed, make sure you like, comment, subscribe, all that good stuff. If you want to see CS interview questions, check out this playlist up here. Otherwise, I'll be making a lot more conceptual CS videos, so keep your eyes out for those. Otherwise, I'll catch you in the next one. Peace.